Hello, welcome to another lesson of sectoral structures theory. Um, Today we will talk about reducible and irreducible sectoral structures, and we will also talk about how to reduce a sectoral structure. We are still really in the first few lessons of the book Sectoral Structures Theory, which is a pretty novel mathematical framework. We're gonna begin by looking at this sectoral structure over here. Let's just focus on the blue parts to begin with. And this sectoral structure can be represented by the sequence 1, 2, 1, subscript 4. So we'll say AN is equal to 1, 2, 1, subscript 4, and we can tell that this has a degree of 4 and it has 3 parts, so it has an order of 3. And keep in mind that for any sectoral structure, by definition, the total length of this curve must be 2 pi. Now, let's look at these black dotted lines here. And we are really just dividing each of these sectors in half. So what will this give us? This will give us the following sectoral structure. It's not the same sectoral structure. They have the same overall shape, but it has more sectors in it. So it will give us the structure 2, 4, 2, subscript 8. We notice still order 3, but now the degree is 8. Now if we look at the green dotted lines, we divided really each sector into 3 parts, or 3 sectors. So this gives us the sectoral structure Cn equals to 363 subscript 12. So we have these 3 sectoral structures. Each of them is made of a different number of sectors, and however we can tell that they all have something in common. They all have the same overall shape, they have the same geometric shape overall, except that the divisions are different. So we will try to find a way to discuss this property. Let's write a sectoral structure in the, using this following format here. We will say AN is equal to WI. I indicates the part, so a given part within the sectoral structure. So for example, 1 would be the first part, 2 would be the second part, and 3 would be the third part. Remember, we call each of these a part. And we will say this goes from I equals 1 to I equals lambda. Lambda is the order of the structure. And we also know that the overall weight, the overall degree of the sectoral structure must be n. So this is another way of to write a generic form for any sectoral structure. We will say AN is equal to WI subscript n from I equals 1 to lambda. Now let's define another property of a sectoral structure. We will call it its greatest common divisor. So the greatest common divisor of a sectoral structure, and remember a sectoral structure is a geometric object, so it's not directly intuitive. However, we're gonna try to simplify it by saying this is equal to the greatest common divisor of all the parts of the sectoral structure. So Wi from I equals 1 to lambda. So the greatest common divisor of all of these parts. Let's look at these 3. So AN equals 1 to 1. So the greatest common divisor of these is clearly 1. Let's look at 2, 4, 2. The greatest common divisor of these is 2. And similarly here, 3, 6, 3, the greatest common divisor is equal to 3. Now this will lead us to our next set of definitions. We will say that if the greatest common divisor of a sectoral structure AN is greater than 1, we will say that this sectoral structure is reducible. If the greatest common divisor of a sectoral structure AN is equal to 1, we will say that this sectoral structure is irreducible. So this is the simplest way to define a reducible and an irreducible sectoral structure. Now keep in mind, some sectoral structures can be made up of a very large number of parts, so sometimes it's not directly obvious whether it is reducible or irreducible. Now next we will define a new operation or function on sectoral structures, which we will call the reduction of a sectoral structure. And we will use the Arabic letter dal, which really looks like this. So it's just like this. So dal will indicate the reduction of a sectoral structure. So for example, if we have a sectoral structure AN and we want to reduce it, we will just place the Arabic letter dal before it. And in this mathematical framework, I used a few Arabic letters because they're not commonly used, and it's a good opportunity to incorporate them. So dal of AN is equal to Wi, which is the weight of a given part I, divided by the greatest common divisor from I equals 1 to I equals lambda, and then it is going to be subscript n divided by the greatest common divisor. So clearly, if it's an irreducible sectoral structure and the greatest common divisor is 1, then this just goes back to AN without changing. A few properties of the dal operation. If we have if we have the initial sectoral structure AN and we reduce it to another sectoral structure, both sectoral structures will have the same order, lambda, and both will have the same walk. If you want to review this in prior lessons, we said the walk is the total linear distance starting from one vertex or one delta joint all the way to the other delta joint. So we call this the walk. So obviously, because these are going to be really pretty the same shape, they're going to have the same walk. Now the curve, of course, is the same, but this is the case for all sectoral structures. The other geometric property is the diagonal, which is the line or the length of the line segment directly connecting the delta joints. So this is the diagonal. So of course the diagonal for the two parts will also be the same. So this is right here. Now the degree will not be the same because we're going to have a different number of sectors, but we will say that the degree of the first sector is equal to the greatest common divisor times the degree of the second sector. Another way to say this is the n1 over n2, so the degree of the first over the degree of the second, will give us the greatest common divisor. Let's look at a few examples. AN, we saw this one, is 3, 6, 3, 12. Dal of AN means that we're gonna divide everything by the greatest common divisor, and we're gonna get 1, 2, 1, subscript 4. And this is the irreducible form of the sectoral structure. Are these the same sectoral structure? No. And we will see why not. They're really not the same sectoral structure, but they have the same properties. If we have the next, let's say xn is equal to 2, 4, 2 squared subscript 10, dal of xn will be 1, 2, 1 squared subscript 5. Notice that the greatest common divisor, we can, if we want to find out what it is quickly, we'll say 10 divided by 5 is 2. Now we said theta structures are simply the ones that look like a pizza divided into equal sectors. So dal of any theta structure simplifies to 1, 1, which is just a circle. So 1, 1. It reduces to 1, 1. Another way to say this is dal of n subscript n is equal to 1 subscript 1. We also saw xi structures, which are made of basically 1 to the power of n subscript n right here. So these are always irreducible. So dal of xi n always equals xi n. So this is the opposite scenario. So all theta structures are reducible except 1, 1. On the other hand, all xi structures are irreducible. Another interesting type is if we have a sectoral structure of the form a to the power of n, so this could be like 2, 2, 2 or 3, 3, 3, subscript a times n. This always reduces to a xi structure, which is I to the power of n subscript n. And for this reason, we will call any structure of this form xi star. So if you see xi star, this type of sectoral structures are of the form a to the n subscript an. Finally, an important property of the dal operation is that once you apply it one time, you've already reached the irreducible form. So if you keep repeating it, you're going to keep getting the same irreducible form. So dal of an is the same as dal of an. Thank you.